So in the last class we stopped at what we did with respect to the points in the northern hemisphere. So you consider these as the points in the northern hemisphere. These are the points which are drawn here in the northern hemisphere on the sphere, and we take the south pole and connect it to the point which intersects the sphere on the northern hemisphere, this point P, let us say, we take it here. And then we take the equatorial plane. So it is again an orange. Now what we do is we take the central part of the orange, cut it open halfway through and take this slice out. That will define the equatorial plane. So this slice is the representation of the equatorial plane. So when we do this south pole to the north pole points, all the points in the north pole are joined from the south pole, and their intersection with the equatorial plane is indicated by the point P. So the little point P here, which is a closed circle, now represents all these intersections. The intersections of the south pole region, the southern hemisphere region, with respect to the north pole now are joined likewise, and that point is indicated by an open circle. So when we have a crystal with this kind of symmetry and do this operation, then we will now slice open this equatorial plane and take it out. Take it out and spread it on the plane. When we spread it out on the plane, we will get diagrams of this kind. So this is now the equatorial plane, and depending upon the nature of the crystal and the symmetry that is associated with the crystal, we will get points associated with the intersection with the north pole, which is indicated by X, and the intersection from the south pole indicated by open 0, or vice versa. It does not matter. As long as we identify the points with respect to the north pole and with respect to the south pole, we keep that identity the same. So this equatorial plane now represents two possible symmetries. You see, we can read the symmetry directly because this now represents the 360 projection. So we have this sphere which is a 360 sphere, and we therefore now represent the 360 degree representation, and we see there is only one point. If there is only one radial point which is emanating into the crystal from that point, we say that the point group symmetry is 1. So this is the projection diagram, and these are called stereographic projection diagrams of various point groups. For every point group, therefore, we can draw these kind of diagrams by taking examples of crystals which belong to different crystal systems and therefore different point groups. So when such studies are made, we will see that in case of the 1 bar system, we will have an intersection with respect to the north pole and the south pole, open circle, and the X point will now indicate this. It not only indicates this, it indicates the relationship between this point and this point. If this point is x, y, z, this point is x, y, z. Let me tell you that clearly. If this point is taken as x, y, z, now this point now is on the opposite side. This is the northern hemisphere, this is on the southern hemisphere of the sphere. So therefore you get minus x, minus y, minus z. So when we get a distribution like this, we identify the position of the presence of a center of symmetry or an inversion center. So this therefore belongs to 1 bar. So we have therefore the stereographic representation of 1 and 1 bar as we see here. So the obvious extension is now to take the crystal systems, associate them with respect to the stereographic projections of symmetry elements, and associate therefore the point group symmetries to each and every crystal system. As we saw in the discussion before, this can be done in this particular table. This is the final result which I will show, but we will discuss each and every point separately with respect to the points which we are going to do. With respect to the diagrams which we are going to do. So what we will do is we will do the stereographic projection on the crystalline systems, and then from the crystalline systems we can take individually the presence of the symmetry elements with respect to the projections we got from the north pole, the projections we got from the south pole, conglomerate these results and see what kind of a symmetry this distribution of open circle and the X points indicate, and based on that we can decide on the symmetry that is associated with the crystal system. So we have now brought in the crystal. The crystal is now 3-dimensional. We have drawn radial lines with respect to the crystal so that they can be represented as a stereographic projection inscribed inside a sphere. So effectively the crystal is taken and put inside this sphere, and we have taken the intersection points in the northern hemisphere. Points are joined to the south pole, and those are indicated by open circle, and the ones which join the north pole from the southern hemisphere are indicated by X points. And based on that we can generate and identify the equatorial plane projection, which is the stereographic projection. And based on the stereographic projection we can identify therefore the point group symmetry that is associated with the crystal. This is the way in which ancient crystallographers used to do. People who study crystals will look at the crystals and do these experiments, and now eventually we will develop a methodology which will tell us how to get this symmetry information on a direct basis. So this now tells us the systems to which we can go into. So this is a general listing, a triclinic system. A triclinic system can have 1 and 1 bar, a monoclinic system 2, 2 bar and 2 by m, and so on. So we will see how each one of them develops with respect to the stereographic projection as we go further. Here is a diagram which shows you the stereographic projections of all types of crystals belonging to these systems. So here are the crystal systems: triclinic, monoclinic, tetragonal, trigonal, hexagonal, cubic, and this is the axis of rotation. So the axis of rotation can take values 1 and then it can take the value of 2, it can take the value of 3, it can take the value of 3, it can take the value of 4. They are grouped together, and the way in which we have organized is triclinic, monoclinic, tetragonal, trigonal, hexagonal, cubic. These are these 5, in fact, trigonal, monoclinic, tetragonal, trigonal, hexagonal. These 5 systems have single axis symmetries, as well as in case of tetragonal, trigonal and hexagonal we can have more than one axis that is present, which is indicated here by individual stereographic projections. So our job now is to study each one of them. We have to study each one of them and understand how the equivalent points are generated. So we will make an attempt today to study a few of them, and in the next class we will take up a few more of them, and then in general we take a few examples from the more complicated looking ones on the right hand side. And then we will go into a representation of each one of them separately, as we saw here, and then as we discussed in the case of stereographic projection, and then distribute them to the various crystal systems. So this looks very complicated, but once we do it and once we revise what we have done, we will see that it can all be fitted into one single understanding of these point group symmetry, the crystal system, and then the distribution of these systems with respect to generation of equivalent points. We have already discussed the generation of equivalent points in case of 1 bar symmetry. For a given x, y, z, there is an x bar, y bar, z bar, and that is in fact illustrated here. You have an x, y, z and an x bar, y bar, z bar. Since this line now represents the line of demarcation and the location of the center of symmetry is here, and because the location of the center of symmetry is here and this is the projection which has been done, we see both of them as open circles. You might be asking why this is one is open and one should be closed, right? Because there is a center of symmetry, and that projection is 90 degrees oriented with respect to this projection. In this projection we are considering the axis of rotation to be 1 and then the axis of rotation 1 bar. So the axis of rotation is the one which is now shown along this direction, and therefore you see this is x, y, z, this is x bar, y bar, z bar, or vice versa. Because of the fact that the center of symmetry sits here, it does not matter whether you have the x, y, z or x bar, y bar, z bar. So that therefore tells you the 2 point group symmetries that can be associated with the triclinic system. So a triclinic system therefore has 2 equivalent points in case we have presence of a center of symmetry, or more appropriately an inversion center, and that inversion center is present at this point where the pointer is shown. Then we go to the monoclinic system, and in the monoclinic system we see that we generate again these 2. Remember, now this is a projection which is showing in a perpendicular direction. Two of the angles are 90 degrees with respect to each other. We can also show this as a two-fold rotation here. Now you might be wondering what is going on here, because this is shown as nothing here, and this is shown as a picture where we have one below the other, and in this case one away from the other. So what is shown here are the two diagrams. It is not necessary to show two diagrams in triclinic because there is no axis of rotation. The moment you have an axis of rotation, we show these are the equivalent point positions and this is the symmetry position. So for every point group, therefore we show two diagrams, and therefore these are the two diagrams which will be shown for each crystal system. So then we will go further into the presence of the two-fold symmetry. As I mentioned that two diagrams now have to be given for each one of these, and this is now showing the equivalent points, this is showing the symmetry position. So this is the mirror operation, and you see that in the mirror operation, I do not know whether you see it very thoroughly here, this has to be a bold circle. This circle is lighter than this circle. So that means the mirror is now flat with respect to the diagram we are showing. So if you see the original textbook, you will see it better. This is from the textbook of McKay and McKay. In fact, there is a proposal from my side that we will give you the handouts. We will discuss with the NPTEL authorities and see, we give a set of handouts for each and every lecture to follow, and that is something which will be very useful for this symmetry class, because symmetry and structure is very fundamental for all areas of science and engineering, and therefore I want you to get a clear hang of these symmetries. So a handout will be accompanying the lecture series. So this now will be the darker one, so it shows that the presence of this. In the case of the orthorhombic system now, we show the presence of 2 by m. This is the presence of a two-fold followed by 1 bar rotation. The two-fold followed by 1 bar rotation generates two possibilities. One is the presence of this equivalent points. Now you see the mirror is in the middle, and therefore this is a presence of a two-fold, and now this is a darker circle. So the two-fold axis is coming towards us. The darker circle is the perpendicular to the two-fold axis. So it is a 2 by m symmetry, 2 bar which is mirror and 2 by m symmetry now represent all the possible point groups associated with a monoclinic system. So triclinic has two point groups, monoclinic has 3 point groups. We go further now into orthorhombic symmetry. In case of the orthorhombic symmetry, we can have 3 two-fold axes mutually perpendicular to each other. That is because we have an A axis, a B axis and a C axis. The angle between A and B and C and A are all 90 degrees with respect to each other. Because we have these 90 degree angles, we will have their two-fold axis along A, two-fold axis along B, two-fold axis along C. This generates an equivalent point diagram of this kind, where you have an open circle and a closed circle, open circle and a closed circle. So the number of equivalent points you generate in a 2-2-2 point group will be XYZ. Then you first operate the two-fold symmetry operation in one direction, let us say along the X direction. Then you will have X, Y bar, Z bar. Then you operate the two-fold along the Y direction, which will be X bar, Y, Z bar. And then you operate the two-fold along the Z direction, which will be X bar, Y bar, Z. So which means that it generates 4 equivalent positions. In case of the triclinic system, for example, we generate 2 equivalent positions, X, Y, Z, X bar, Y bar, Z bar. Please note that this picture, I do not know how clear is there up there. This is a closed circle and this is an open circle. Do you see that? No. So this diagram is not that very good. I will be showing it more detailed in the next set of diagrams. So the presence of the 3 intersecting two-fold axes now generate the symmetry disposition. These are the symmetry disposition diagram, where you see there is a two-fold along this circle, the two-fold along the direction along X and direction along Y. So all 3 directions have the two-fold symmetries. So this represents 2, 2, 2. Now the combinations of 2, 2, 2 can be 2, M, M, because we can have a proper axis, an improper axis, and followed by another improper axis. No other combination is possible, which we have discussed much earlier, several classes ago. So this can be 2mm, or 2mm is same as mm2 and m2m, because A, B and C in an orthorhombic system are interchangeable. You can always call A as B, B as C and C as A, because the only condition we put in orthorhombic systems is the condition on alpha, beta, gamma being 90 degrees. So we can interchange A, B and C. So this represents a common representation where we have A and B directions associated with the mirror planes and the C direction associated with a twofold. So the symmetry diagram is up here. It tells now these are darker, as you can clearly see, that represents the mirror. So one mirror here, another mirror there, and the C direction which is coming towards you has a twofold symmetry. So the equivalent point diagram again is shown here. This should have therefore, how many do you expect as the number of equivalent points? In this particular case of 2, 2, 2, we are expected 4 equivalent points. In case of mm2, we expect again 4 equivalent points. On the other hand, when we have a symmetry which is mm actually represents 2 by m, 2 by m, 2 by m, and therefore you will have number of equivalent points as 8. 4 up and 4 down in this diagram, 4 up and 4 down, that is total 8. And this now becomes all dark in the sense that there are 3 mirrors perpendicular to each other. The presence of the mirror and the angle 90 degrees will invoke automatically the twofold axis along all 3 directions. So there are perpendicular twofold axes coming towards us, then the mirror planes which are intersecting in all 3 directions, and that represents the highest symmetry that is possible in case of an orthorhombic system. So today we have covered the triclinic, the monoclinic and the orthorhombic systems. We have shown how the equivalent points develop. The next thing is we will have to see how the tetragonal system develops. In case of the tetragonal system, we now look at the possible symmetry positions which are coming with respect to the operation. So as we go back here, x represents the rotation axis. So there is a 4-fold rotation, there is a 4-fold rotation with a mirror combination, that is with an inversion combination which is 4 bar symmetry, and we also have a 4-fold rotation which accompanies a mirror symmetry. These are single point operations, that means these are single symmetry operations. The moment you have a 4-fold symmetry, you will have also the presence of an inversion center associated with it. Just like the monoclinic system, you had a 2-fold symmetry, you had a 2 bar symmetry. So with 4 we will have a 4 bar, and we also have a 2 by m, therefore with 4 symmetry we have a 4 by m symmetry. Now these represents again the equivalent points on the left side and the symmetry diagram on the right, and this therefore represents the tetragonal system. The tetragonal system can also have more than one axis. The fact that we have these orthorhombic systems which have more than one axis, proper, improper and so on, applies to these systems as well. And therefore in a tetragonal system we have 4, 2, 2 and 4 mm, just like we have 2, 2, 2 mm2, we can have it 4 mm, because we always represent the z axis to be associated with the 4-fold rotation. The moment the z axis is associated with 4-fold rotation, we will have this issue of 4 mm, and that is unique, whereas here mm2 could be 2 mm, m2m and so on. So because we have 4, 2, 2 and 4 mm and we have this 4 bar symmetry, 4 bar symmetry will give rise to 4 bar 2m and also 4 by m, 4 by m, 4 by m, where we have the combination 4 by m, 2 by m, 2 by m, which is now representing the overall highest symmetry that is associated with a tetragonal system. So the tetragonal point groups are 4, 4 bar, 4 by m, 4, 2, 2, 4 mm, 4 bar 2m and 4 by mm. So 1, 2, 3, 4, 5, 6, 7. So 7 point groups can be associated with a tetragonal system. Monoclinic has 3, orthorhombic has 3 and triclinic has 2. So this left hand side of this slide now covers 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have covered 15 of the possible 32 space groups by going from triclinic to monoclinic to orthorhombic and lastly to tetragonal system. Now on the right hand side is the remaining crystal systems. The remaining crystal systems, we already see that hexagonal and trigonal are a little complicated in terms of having both the 6-fold as well as the 3-fold. So it depends upon where the origin is and where the 3-fold and the 6-fold are located in these compounds. It is not necessary to have a 3-fold symmetry and a 6-fold symmetry looking one and the same. Obviously it is not, as you see from the equivalent point diagram and also from the diagram which we have drawn on the right side. So this gives rise to the 3-fold symmetry, a single rotation axis symmetry, which will give rise to 3 bar. Now as far as the 3 and 3 bar are concerned, these operations now introduces this translation symmetry, which is not half or 1/4. Because the translation symmetry is not half or 1/4, the issue comes up with the point group symmetry, because we have to have the definition of a point group. That means when we start generating the points with respect to these operations, they should come back to the original point. That is the definition of a point group. So if you start from, in this example, if you start from x, y, z, you go to x bar, y bar, z bar, you have to come back to x, y, z by operating it again. So that repetition of operations will occur in case of 3 and 3 bar, but they will not occur if we consider the case of 3 or 3 bar by m or 3 by m. So that is because of the fact that the 3-fold axis appears at a rotation distance, at a uniform distance of 2/3 and 1/3 from the axis. And the location of the 3-fold axis, in the case of the 6-fold axis, again there will be 3-fold axis which will be located at 1/3 and 2/3. And therefore we will have, in this particular case, no possibility of extension of 3 and 6 being same, and therefore 3 bar and 6 bar are different from each other. Since 3 bar and 6 bar are different from each other, we can have a combination of 6 and a mirror perpendicular to it. A combination of a 3-fold and a mirror perpendicular to it is not allowed. This is something which we probably will give you as an assignment. I don't know, but I think it could be a heavy assignment in such situations. We will worry about that fact, whether we can, you will be able to digest that as an assignment as we go along. But the fact remains that with the trigonal as well, and along with the hexagonal system, we should have the more than one axis intersecting at a point. When we bring in that issue, we will have these additional point group symmetries 3-2, 3m and 3 bar m, and the equivalent point diagram is on the left and the symmetry diagram is on the right, and that is illustrated for all these hexagonal systems as well as from the trigonal systems. Because of the fact that 3 and 3 bar create problems, we do not have a 3 bar m2 here, and therefore we have 6, in fact we have 5 trigonal point groups and 3 plus 3 6 plus 1 7 hexagonal point groups. Cubic system is quite complicated, as we saw in the earlier classes also, because of the fact that the axes do not coincide with A, B or C. The only axis which coincides with A or B or C is the 2-fold axis, which is a redundant operation in a cubic system. And the issue that the cubic system axis should not appear either along A or along B or along C, the symmetry that is required is also very crucial. And therefore we generate very complicated diagrams, stereographic diagrams, as is shown here. We will probably spend a little time on this or not, we are not sure as we go along, but these can be studied with respect to the tetrahedral and the octahedral distribution we discussed in several classes ago. We did talk about the way in which the distribution occurs when we discussed individual rotation axes, and then brought in the issue of the location of these rotation axes. And with respect to that, therefore, we now have a total of 32 point groups. And this, I think, is more or less the stage at which I would like to end here.